My name is Arya Murugan. My registration number is RA241102601135. Today we'll be exploring the concept of CPU scheduling, a fundamental part of how operating systems manage processes. In this presentation, we'll cover what CPU scheduling is, its objectives, the main types of scheduling algorithms, and key terms you need to understand to grasp how these systems work effectively. Let's dive in. What is CPU scheduling? It is a core function of an operating system that manages the allocation of the CPU to various processes waiting in the ready queue. Since many processes require CPU time, but the CPU can only serve one process at a time, the scheduler decides which process should execute next. This decision making happens frequently during a system's operation, especially when processes block for input output, terminate, or when preemption occurs. Effective scheduling is crucial to keep the CPU busy and maintain overall system efficiency. Now let's talk about the primary goals of CPU scheduling and its objectives, which includes maximizing CPU utilization, which means keeping the processor busy as much as possible. At the same time, the scheduler tries to maximize throughput or the number of processes completed in a given time. Minimizing turnaround time, which is the total time a process takes to finish, is also important to improve user experience. Additionally, the scheduler aims to reduce waiting time, the time a process spends waiting in the ready queue, and response time, which is especially critical for interactive systems where quick feedback is expected. Finally, fairness is key, ensuring no process is starved of CPU time. Now, there are two main categories of CPU scheduling: preemptive and non preemptive. In preemptive scheduling, a process can be interrupted and moved back to the ready queue to give the CPU to another process. This allows for better responsiveness and is common in time sharing systems. Examples include round robin and shortest remaining time first algorithms. On the other hand, non preemptive scheduling allows a process to run until it either completes or blocks for input output without interruption. It's simpler to implement but may cause longer waiting times for other processes. For example, first come first served and shortest job first are some examples of non preemptive algorithms. Let's look at some key terms. First is CPU burst, which is the time a process spends using the CPU before needing input output. Alternates with the input output burst during execution. IO burst, time a process waits for input output operations to complete. The CPU scheduling only happens during these CPU bursts. And turnaround time, which is the total time from process submission to completion. To calculate this, we subtract the completion time minus the arrival time. Some additional key terms are waiting time, which is the time a process spends in the ready queue waiting for the CPU. The formula is turnaround time minus CPU burst time. Next is response time, which is the time from process submission to first CPU execution. The formula is first CPU start time minus arrival time, and it is crucial for interactive systems. Finally, there is completion time, which is the time when a process finishes execution. To wrap up, CPU scheduling is essential for managing how processors share the CPU efficiently. Scheduling can be preemptive or non preemptive, each with its own advantages depending on the system's goals. Metrics like turnaround time, waiting time, and response time help evaluate how well scheduling algorithms perform. And ultimately, effective CPU scheduling improves the system's speed, responsiveness, and fairness, leading to a smoother and more balanced computing experience. Thank you. And now on to my friend Debrup Nandi, who will take us into
Hello
these
guys,
scheduling
my name is Devrip
algorithms.
Nandi and I will be covering scheduling algorithms. FCFS schedules process strictly in their arrival order like a queue or a counter ticket. Once process starts, it runs completion without interruption. This simply can lead to long waiting times if short jobs wait behind long ones. Non-preemptive (SFJ) chooses the process with the shortest burst time from the ready queue and runs it until it finishes. This reduces average waiting time, but longer jobs may suffer starvation if job keeps arriving. In preemptive SFJ or SRTF, the CPU always runs the process with the shortest remaining burst time. If a new shorter process arrives, it preemptively runs the running one. This improves responsiveness but increases context switches. Round-robin scheduling aligns the CPU to each process in a fixed time slices called quanta, cycling through all processes in a circular queue. If a process doesn't finish in its time quantum, it's moved to the back of the queue and waits for its next turn. This ensures fairness and responsiveness by giving each process regular CPU access through frequent context switching can add overhead. Thank you for watching. Over to Shikha for the next part.
Hello, I'm Shika Naveen Kumar, register number 371 from AJ2, and I'll be covering the performance and comparison aspects of CPU scheduling. In this part, we'll look at how we measure scheduling efficiency, compare the main algorithms, handle problems like starvation, and finally see some real world applications before wrapping up. Slide 1 is performance criteria. Whenever we evaluate CPU scheduling, we use certain performance metrics. First is CPU utilization, which tells us how busy the CPU is. Ideally, we want it close to 100%, but practically it stays around 80 to 90%. Second is throughput, the number of processes completed in a given time frame. More throughput means more efficient systems. Then comes turnaround time, which is the total time a process spends in the system from submission to completion. We also look at waiting time, which is how long a process is stuck in the ready queue. Lower waiting times are always better. Finally, response time, which is especially important in interactive systems, is the time from when a request is made until the process first gets CPU attention. Together, these factors help us decide whether a scheduling algorithm is performing well or not. Slide 2 is comparison of algorithms. We will compare the four main algorithms. In first come, first serve, processes are held in the order they arrive. It's simple and fair, but one long process can delay many shorter ones. In shortest job first, we run the shortest task first. This minimizes average waiting time, but it can be hard to know in advance how long a process will take, and longer jobs may get ignored. Next is priority scheduling, where processes are given priorities. High priority jobs finish earlier, which is great in critical conditions, but low priority jobs may starve if new high priority ones keep arriving. Finally, is round robin, which is very common in modern systems. Every process gets a small time slice, then the CPU moves to the next. This is fair and responsive, but if the time quantum isn't set properly, performance suffers. So each algorithm has strengths and weaknesses depending on the type of system. Slide 3 is starvation and aging. One big issue, especially with priority scheduling, is starvation. This happens when a process keeps waiting indefinitely because new high priority processes keep arriving. For example, imagine a low priority background task on your computer. If important system tasks keep coming, that background task may never run. The solution is aging. With aging, the longer a process waits, the higher its priority gradually becomes. Over time, even a low priority process gets a chance to run. This balances efficiency with fairness and ensures that no process is ignored forever. Slide 4 is real world applications. We shall see with these algorithms and how it's used in real life. FCFS is commonly used in simple batch systems like print spooling, where jobs are completed in the order they're received. SJF, it works best in batch processing systems where job lengths can be predicted. For example, data analytics tasks where simple queries are finished first. Priority scheduling is very common in real time operating systems. For instance, in a hospital system, an emergency alert or patient monitor gets higher priority over background tasks. Round robin used in modern operating systems like Windows, Linux, or Android, where multiple applications are open. It makes sure each application gets CPU time fairly so users can feel the system is responsive. These real world uses show why different algorithms exist and each fits specific needs. The last slide is conclusion and summary. To conclude, there is no single scheduling algorithm that is the best in all cases. Each has its trade offs. FCFS is simple and fair, but inefficient for varied job sizes. SJF is efficient in reducing waiting time, but impractical if we can't estimate burst time. Priority scheduling gives flexibility and ensures critical processes are handled, but without aging, it risks starvation. Round robin is the most balanced for time sharing and multitasking, but it relies on choosing the right time quantum. The main takeaway is that CPU scheduling is always about balancing efficiency, fairness, and responsiveness. The right algorithm depends on the system's goals, whether it's throughput in batch systems, responsiveness in interactive systems, or fairness in time sharing systems. Thank you for listening, and that wraps up my section on CPU scheduling performance and comparisons.